After seeing yesterday's presentation, I decided to change my topic because if you are still interested in the topic about magnetic connection, I will talk to you privately. There's too much material to present. I down-selected two things that will be most interesting for this audience. I have lots of collaborators. I want to encourage all of them, but maybe during the talk, the citation will show up during the presentation. And also, I want to thank the organizer to invite me. I see lots of young faces and also old faces. I counted how many people I really know. So about 10 people out of 60. So that scares me. That means most of the people don't really know me or my work. That's why maybe reaching out to people who don't really know about you using this jargon, which is my goal here. To people who I already know, please forgive me for repeating something that you already know. Also, the organizer, she's not come back yet. But she was a student when we had a center called the Center for Magnetic Self-Organization. The Carrie talked about that also this morning, 42. And she was a student, Alex Nazarian, and she was a youngster at the time coming up. Now she's organizing the whole thing. So we're really happy to see the next generation doesn't come up by cooperative research between laboratory plasma physics or fluid dynamics with astrophysics and geophysics. Okay, so I want to start with this comment. And about 15 years ago, I was in the audience, Stephen Chu was giving a talk. He was a kind of physicist at that time, but he's changing the field to biophysics. He made a comment that biology and astronomy is retirement physicist. As it happening in this conference, the CCA, CCB is really a mirror of the two biophysics and astrophysics. This is both merging of two different fields into a new subfield science. And we see lots of collaboration going on. So I want to be part of that. I'm happy to be part of that. So this is my outline. I want to be very brief in terms of introduction. However, I want to use as name and language as much as possible. Why we bother to do experiment? What's the idea and the realities? And mainly two results. One, hydrodynamics. The other one is magnetohydrodynamics. And then I want to point out quite a few future possibilities for potential collaborations for this audience. Maybe some of them can resonate with me. And people, you weren't here, I was commenting, we're happy to see you here. And we can start thinking about the collaborations. I have 4 possibilities I want to point out. So before that, the hydrodynamics part, in compared to hydrodynamics, one question was, is the nonlinear hydrodynamic instability really exist? If it does exist, can they effectively transport angular momentum to expand fast accretion we see in accretion disks and in the quasi-Keplerian or Keplerian flows? The answer so far is pretty firm no. And then using the hydrodynamics, we have succeeded to demonstrate so-called magneto-rotational instability, which will be subject for the magneto MHD, but also you can do a demonstration by mechanical spring mass analog, which is quite interesting, and you can do that in the classroom. And then this is MRI in magnetohydrodynamics is quite complicated and difficult. I think finally we have got some relevant data I want to show you towards the end. So start something very too simple, maybe. And some of them for geophysics or fluid dynamics, probably want to know the definition. The accretion disk is a disk structure made of gas, dust, and plasmas, and rotating around a central object, gradually fall into the center. It's called an accretion process. This is not a real picture. It's somebody's imagination. But real picture is taken by the ARMA observation from the recent couple of years. And it really is imagine the dust density from the star-forming disk. And you can see the structure already. So there's a very interesting astrophysical process taking place in such a disk. This is the star and the planet being formed. So the accretion disk is placed for this. The other one is mass transfer energetic activity between in the binary star. I couldn't find a real picture. This is an artificial picture. A material from one star can be sucked into the other star through accretion disk where energy can be released. The third one is the center of the many galaxies, and that's a real imaging, but it's too big to see the accretion disk. You see a torus, but the disk is maybe tiny there. But they are very, very powerful. They can outshine the whole the star, one particular galaxy, not in our Milky Way, but the other galaxies can be as bright as 10 to 15 the sun. This is probably the most luminous steady source of the universe. The transient one is a gamma ray burst, of course, but this is the steady state in all time scale. So why they even shine? So there's efficiency, the conversion of energy from gravity to the photons, that's why we see. So this is the thing about the actions around us, how to convert energy in the unit of mc squared. So chemical reaction is very inefficient, by the way. They are only convert minus 10 to minus 10. But solar type star accretion, you get 1 million of it. That's pretty good. Nuclear fission is the one we use electricity. It's getting much more efficient. Nuclear fusion, many people in quantum physics are working hard on this. It's more efficient than fission. But accretion to compact objects is much more efficient than anything else. And of course, you can compete with annihilation matter, but we don't use that for energy production purpose. That's why it's so bright in the universe. But this means important. We have to worry about why they can even shine, because the angular momentum conservation prevents you to go to the gravitational potential. So you have to have a mechanism to remove the angular momentum so that it can go to the potential, gravitational potential, release the energy. So the motivation for my talk is the astrophysical questions, and often they are motivated observations. For all cases, how to generate turbulence, but simple viscosity cannot be efficient to remove angular momentum from the orbiting gas or plasma. You have to have a turbulence to be efficient to transport the angular momentum out so that the material can fall in. And that is a motivating question. There are competing theory ideas. So sometimes it's microscopic. You cannot really see. That's why it's a problem. For this case, we have two competing ideas, roughly. The magnetic rotational instability, in short, MRI. Don't be confused with another MRI, which is, if you Google MRI, it shows up in many other MRIs. But this MRI is a particular MRI for astrophysics. And there should be a working a theory idea in hot and magnetized accretion disks. But in cold and a very dense like star-forming disks, the plasma effect is not that important. Then the nonlinear hydrodynamic instability can be a viable candidate to generate turbulence, like I heard about yesterday, like pipe flows. And it's very hard to test the idea through observation or numerical simulations. The parameters are far away, the observation is very unresolved. That's why sometimes experiment can contribute. So the idea for experiment is, can you create such a flow in the lab? So to satisfy so-called Keplerian or quasi-Keplerian geometry. So the inner speed has to be faster than the outer speed. So, but angular momentum, the inner speed, has to be smaller than angular momentum, the outer speed. So it should be stable for radial instability. Sometimes it can be called as the centrifugal instability. With that configuration, you can ask what's the instability, but we realize we don't have gravity in the lab. So you have to have a wall to hold this balance the centrifugal force to achieve the so-called force balance. So for the MRI case, you want to have a conducting fluid. We're using liquid metal with imposed magnetic field, vertical direction. And for the nonlinear hydrodynamics, we can use water. So this is a typical geometry. The inner cylinder rotating faster than the outer cylinder. You can use liquid gallium in our case, or water in between to depend on the question you want to ask. If we look at, it's a Taylor-Craig flow. If from fluid dynamics, you learn from the textbook. It's not very new. It's more than a century old, and both Taylor and Quet contributors to the field. Actually depends which country you come from. You have to call it Quet Taylor or Taylor Quet. And be careful. Actually, I was a little bit surprised to hear that. But you can learn lots of nonlinear dynamics bifurcations from this. You can see the flow can transition one state to the other state with gradual progression towards turbulence. That's why it's very rich. You can study a lot. But this is experiment or simulations or theories is done so-called centrifugally unstable or really unstable regimes. Not the almost nothing about the quasi-Taylorian regimes that is described on the previous page. So that's the idea, but it turns out the reality is much harder because there's no binding energy gravity due to the boundary, required boundary. When boundary comes in, the geophysical effect will come in. So this is so-called Ackermann circulation for people who know geophysics. So you have, say, rotating flow like your teacup, and usually in the bulk of the tea or coffee, you have a balance between pressure force inward from the wall and the centrifugal force trying to go in the rotating frame to outside the balance. But on the boundary, on the bottom of the tea, they lose the balance because viscosity slows down the rotation, but pressure force is still there. Therefore, force is imbalance, and there's a converging flow towards center. That converging flow circulates. That transports the angular momentum much more effectively than the instability you need. So that's the one is happening in our experiment because we have end caps, top and bottom. It forms two Ackermann cells that becomes a part of become a mechanism to transport angular momentum. Jeopardize the setup, and we wanted to do the experiment. So this is really harmful because you have to really overcome the effect. It causes lots of confusions and understanding. But later on, after so many years work on that, and we realized that can be helpful if you use it for our advantage. I'm going to show because the end cap we have, we can use it, the material that we want to use. For our MHD case, we can use electrically conducting end caps so that you can inject the free energy to energize more the MI than needed from normally from radial direction. So we can have larger MI amplitude using correct way of injection the free energy from the actual boundaries. Okay, so come back to the question of the hydrodynamic turbulence. We see that picture over again yesterday, and we don't have to repeat everything. But the beauty of that is the engineers use it all the time. This is a Moody diagram that this is since the 1940s, and they composed lots of experimental data, show the frictional force. Remember, the fraction of frictional force goes down with Reynolds number, but about 2000 something, the sudden onset, some turbulence. And that increases the friction hugely. It depends on the roughness of the wall asymptotes to different values. That is the picture people use to, well, if that turbulence happens in a pipe flow, why not in a accretion disk? So the question number one for us is, really the same mechanism exists in accretion disk? If do, what's their efficiency? So, but that tends to be very contentious theory debate because it's hard to measure right there, but you can think about all kinds of different theories. And right now, at this moment, I think all the converge to answers no. So I listed all the theory number paper here. I hope I didn't miss anything. Stefan Starowitz in 1981, he used the same pipe flow analogy, speculate, should be, maybe yes, because he didn't really prove anything, but probably the idea. In the 90s, many people follow up, some of them using numerical simulations and trying to test the idea. They come out with the very rough way to say yes or no, maybe yes, maybe no. And many people in the early 2000s and work on the problem, most are linear, by the way. How much stretching the perturbation amplifies the initial perturbation, and then hopefully have a nonlinear transition to turbulence. So the people were working hard. But until nonlinear simulation shows it's very hard to do. Then, but people still continued until most recently, And that most recent part is interacting with the experiment. So experimental size actually being Richard Zhang, they are the first one to use Terracret to test the idea. They had the conclusion, maybe yes. And then Howard Beckley and Sterling Colgate in Los Alamos, they did a similar thing by measuring torque. They point to maybe no. Then we came in play, and we did a spin-down experiment, showed that spin-down time is really nanometer. So we said, oh, maybe no. Then within year 2, we built a new experiment, we can show quickly, that actually by measuring radial stress in that flow is really, really tightly. It's like a noise level. It's very hard to find any evidence is yes. So we concluded no. And then that wasn't end of story. We thought that we were down this experiment conclusively, but 6 years later, we had the counter experimental data should be yes. That motivated us to come back and revisit the same question, but with different device, different techniques. I'm going to show you. And I showed us still no. And we were communicating with the other group. I think we converged. The answer right now is no. But could be surprised. You never know, right? So this is the device we constructed. And the reason the way to counter the Ackermann circulation is by break up your end caps in different pieces, each of them rotating different speed, so that it doesn't create a force imbalance in a big way, so that an Ackermann circulation is breakdown. So physically, we construct this kind of device and put it together and we operate it. In terms of simulation, to illustrate how it works, without breakdown, you have 2 Ackermann circulations, the transport angular momentum. With breakdowns, you can break to small eddies. The small eddies are localized at each edge. The middle is kind of unaffected. So that is the idea. So we did a Reynolds stress measurement in about 2006, and we showed this is normalized Reynolds stress as a function of Reynolds number. Is calculated based on shear Reynolds number, not simply speed notation. To show this is solid line is viscous stress. So this is a measurement. If you do correctly, it all becomes 0. If you don't do correctly, which means you choose different speed, not to break down the Ackermann circulation. It can be large, it can be huge, and that's what you need for astrophysics. So you have to be careful. And then when I talk about 6 years later, if we translate their measurement into same diagram, they got the data like this. This is just about right to explain the accretion they needed. But we realized later on, their end caps are still attached to outer cylinder, even though they are far away. So it's a new experiment built based on their input. So instead of 2 rings, we break down into different on a 1 ring, so getting a little simpler, but also have active perturbations. So we had the 24 nozzles to actively agitate the flow. And then you question what kind of function you choose to perturb the flow. In the pipe flow case, there are preferred perturbation patterns that we know. Here, there's no theory. So what we did is just brute force. So we tried all different perturbations, helical, non-helical, in one height, different height, and up with tedious systematic approach. We tried a couple thousand different kind of combinations. And I'm always like this. So this is a perturbation as function of time. Whenever the perturbation is on, it's like a 20% perturbation is huge. When you turn off, it immediately becomes quiet. And if you do solid body, actually come down much more gradually. So being shared, even though shear is huge, it's free energy source. Actually, it's a good thing. It cures your perturbation more effectively than solid body. Yeah. So we kind of confirmed that the previous experiment is still correct. And we did self-similar scannings to make sure when Reynolds number is increased, the similar behavior persists into higher Reynolds numbers. So that was the end of the experimental side. But numerical progress has made in the past couple of years. And most notably, Lopez and Avila in 2017, they was able to use the exact same geometry, the new device we have, by increasing shear Reynolds number to 32,000 progressively you see the localization of turbulence towards the end caps. And that is consistent with our experimental picture. You can see, I don't know if you can see, perturbations are localized here rather than here. When you run experiment, you can see immediately there. But once you see the picture, it's getting harder. Yeah. So there's a question to the fluid dynamics community. The when higher number shear flow cannot be, it's not turbulent. It's anti assumed today. But the question, actually Steve Babas wrote this one, the comment, the focus on the fluids. He asked, there's a grand challenge problem for fluid dynamics. Yeah, there's lots of evidence against turbulence for such a special flow. Is there any way it can be done to prove that, or even proving it such a way is valuable when such a turbulence cannot exist in such a special flow? And actually, I was, for the curiosity, and I was talking to the fluid dynamics, many of you may know Bruno Eckert. He is really an analytical theoretician in the fluid dynamics community, talk about how to prove things more rigorously. But I was shocked to learn, sad to learn, he passed away the past summer. So we lost really good friends who can really work the problem, maybe solve in a big way. I hope someone else in the audience may be interested, continue the journey that we've been taking so far. But also, interestingly enough, when we look at the atmosphere flows, the vortexes like we heard about yesterday, and then like hurricanes, often they're taking similar profile. This is a picture of the data taken, it's 1988 hurricane. There's an airplane measurement flying through the hurricane called Gilbert. They measure the velocity profile. The I is kind of solid body notation. Outside I is quasi Keplerian. So maybe there's a commonality why Keplerian flows are preferred and why it's so stable, robust, and not destroy immediately so that they don't, maybe nice you can destroy it. So that's maybe the question. Okay, I got to move on. The second question is the MI, the magnitude notation instability. Does that instability exist in the quasi-Keplerian flow? If it does, how much angular momentum transport it can provide? That turned out to be a very, very difficult experiment. So it's not very conclusive yet. There's a list I have. The not of simulations theory. I don't list it anymore because it's too much, too many. And this is the effort devoted to this experimentally. So they did a false alarm in the spherical geometry in early 2000 that said they saw MI. It turned out it's not by simulations. Then in the Germany group, they had the helical MI, and also later on the so-called azimuthal MI versions instability has been confirmed. Those are instabilities at very low Reynolds numbers, but unfortunately, it's not probably not applicable to disk due to the profile requirement. Using polymers, yesterday we heard about is the polymers putting the tetracret, they can generate instability. It's analog to MI, has been done actually with Wisconsin Borlev et al. Then we also made a progress on this one. Turned out that some other instability shows up. I'm going to show a picture of that. Then Kerry I don't know if Kerry said that. You made an effort trying to do plasma credit experiment. That was interesting, and I was.
They're still ongoing.
It'll be interesting because that would be really aim for a different regime, in a very called a whole MHD regime for MI. This never done before yet. So this is another effort. Then recently we used the conducting boundary, as I said, trying to inject more energy into the system so that the MI can grow bigger, so we can detect that. But also we demonstrated the MI mechanism by the mechanical analog. So what is a mechanical analog? So people who using imagination, you can easily say there's a star in the middle. If there's two planets, suppose they're linked by a Mach field, which is a spring. If there's a perturbation to one of the planets inward, they have to rotate faster by Kepler law. They can stretch the spring. When you stretch the spring, you're losing angular momentum. losing angular momentum, you have to go closer to star because you're losing angular momentum. They can stretch more the spring. It's a runaway process. So the runaway process between the dynamic two stars can be described by the perturbation x and y in the rotating frame, and it can derive equations very easily. And this is the coriolis force, this is time diminutive, this is spring constant, this is the gradient due to the Capillarian force. It can, assuming do typical k omega dispersion calculation of the waves, you can see the dispersion relation like this. That is exactly the same, the MHD, ID-MHD dispersion relation, except the spring was replaced by main field effect. So that really mirror mechanical analog with MHD. So that actually was tried or a hydro experiment. We replaced the one planet with a post because you don't have to be same two planets. It can be very heavy, so heavy it doesn't move at all. But the other planets linked to the post with a spring. So this is the picture. We put a post here with spring linking the one ball with a camera immersed in water, which is the quasi-Capillarian force. There's a picture of how big they are. There's a picture of looking from up, and it can derive the equations a little more rigorously, taking into account, the polar coordinate, using the drag force for Stork and Reynolds, because there's the interaction between ball and the fluid. You can solve the equation almost exactly, predict the trajectory even though the initial conditions. So we did experiment. This is a movie taken by camera. Two of them superposing each other, one with spring, one without spring. So the red was a ball, and we are in the rotating frame. So the one ball went off, the other one, and you can see a little bit of spring here if you sharp eye there. So we can analyze this time evolution of the ball location and the speed. Oh, it's repeating here, I guess. Okay. So you can really plot out time evolution of the, everything. So it's polar coordinate. In solid body, everything's boring. Nothing happens. You go azimuthally, and the radius is the same, and the angle moment doesn't change. But if it's quasi-Capillarian flows, the three different conditions give three different curves. So the color coding, so the weak tethered is an MR case. So that goes down, the red one, but that go radially inward, like when losing angular momentum. And radially outward, they gain angular momentum over time. And then it's a solid body. There's a strong tethered. If too strong, it becomes one planet. It do nothing. This is so-called blue. A blue, maybe that little kick off at beginning, but doesn't increase anymore. If no tether, it's black, and it becomes conservation angular momentum is being shown here. So you can see by compare the three cases, and it's easy to see the effect of the spring, therefore the MI mechanism. Okay, in the interest of time, as we move on, I want to do this future possibilities. So this is the first try. We have to convert to a liquid metal and have ultrasonic measurement of the azimuthal velocity, a function of time. There's a little movie. We immediately see some things going on here. And when time goes on, when main field starts imposing, you can see the spiral of perturbation shows up. And this is exciting, some instabilities. But unfortunately, that's not the MRI. It turned out is Kelvin Holmes instability of a free shear layer in the middle of the liquid metal created because the jump of the actual boundary with the main field combination create a free shear layer, which is unstable for KH mode, becomes spiral. And we did linear simulation theory and nonlinear simulation matched almost exactly. That's why we know must be free. It's not the MRI, and this was it can be very confusing if you know something is synced to the MRI. It's not. So, but we also realize that the insulating bounding condition is not good enough to influence the flow. So we decide, with suggesting our collaborator from Germany, we should, using the boundary condition for advantage, by using conducting boundaries on top and bottom to create the shear in the omega shear in the fluid is unstable to MI. So we built the experiment with a copper plate, a little messy there. And we did the experiment comparatively with insulating conducting cases. And you can see it's very different. It's much more effective, very quick, at very high frequencies. You have lots of fluctuations. Then we also used engineering code called Sphinbang. It's a very used engineering MHD code with flexible boundary conditions. We are able to compare the measurement with simulations. And with the insulating ones, we didn't get agreement for the main field on and off because the viscosity in the experiment in simulation is wrong, because by factor of actually factor of 5 difference. But in the conducting case, despite the difference, we get everything agree in terms of profiles. It's because when the end boundary is conducting, you have a current in and out from liquid metal to the boundary. That's dominating viscosity. That's why conducting is effective. And if you capture that right, even the viscosity is wrong, you get everything right. So with this, so finally, we're able to march into so-called MI predicted regime after so many years of effort. So this is a summary plot. That's omega. This is like a Reynolds number, mega Reynolds number. 2500 is maybe like a 4 or 5-ish. Here is main field strength. So the blue line is linearly predicted unstable case boundaries. The color coding is growth rate. And that's gray dots is simulations. And the prediction of how much main field, the radial main field you measure due to the instability, whatever, in the system. You can see becomes bigger. But go beyond the linear instability. So that's something we don't really know. Maybe it's nonlinear effect. The experiment-wise, we see also huge, by the size of dots is size of signal. So we see lots of expected results inside this region. But surprisingly, we see also larger dots around outside here. So we're in the middle of trying to figure out which one is which in terms maybe there's a mixture of different instabilities or maybe nonlinear effect. So we're trying to figure out, but it must be MI must be part of that already. So what I want to interest in is, suppose there's multiple contributions, is there any data science techniques we can use to separate classification with different kind of effect? So I'm curious with that kind of question, come here, and if any suggestion, I would be willing to hear whatever you can suggest. Okay, so I just skip that to summary and give to, okay, we already went through the 2 questions. The future possibilities, I have 4 listed here. One is you can, as the next step, it'd be nice to do MI turbulence. You have multiple modes, you can really do a turbulent experiment, but require end caps to drive more effectively. The 3 other possibilities, maybe it's tested overlays. Rossby wave turbulence with zonal flow interactions. This is one I want to show you a slide here. So we can modify experiment like a beta plane approximation, and it can have slope, have injection like this in and out, and with solid body notation, it can generate zonal flows. So this is solid body flow. After perturbation, you get zonal flow. But turn out to be that's due to the asymmetry of 2 nozzles in and out are not symmetrical. So we have to be careful what is the technique we're using. But if we dial down the flow drive, I think we can get rid of this asymmetry. And then the next step is trying to cooperate with the solar physicists, see if we can study so-called near surface shear near that we measured by solar solar seismology. There's shear of solar rotation around surface size where measured. We don't know where it comes from. The idea is the Rossby wave turbulence can drive that. And then we go back to the. So we are also did something that's throwing at the gas and plasma experiment for the non-compressible hydrodynamics, the gas dynamics, or Hall and polar diffusion regimes. Also, lastly, I want to show that maybe there's a possibility to rapidly rotating turbulent convection. I want to show that. for our fun, maybe. This one. So this is really number, a definition there. Then Coriolis number, which is over there, is how much speed you can notate. The idea is we have lots of rapid notation already. We need to impose temperature gradient to drive convection against gravity. So if we do this diagram, you can see lots of planets or solar system in very rapid rotating regimes. This line is predict the transition from non-rotating to rotating convection, and most of them are rotating convection. So the question is, can we do experiment in that side of the regime? The two possibility: we can upgrade or tinacret by import temperature, or the ultracentrifuge, which is very fast in gas centrifuge, and you can do a compressed gas. It's pretty complicated experiment. It will be another 20 years needed maybe. So, but in principle, if design out, it's not too far from really, if somebody really have, maybe I don't have enough energy or time to do this, but well, who knows? Somebody have a good idea. So we brainstorm about this kind of things with our engineer colleagues in Princeton, and also our German friends who are really interested in this called ultimate turbulence of the convection. I'm sorry, I didn't meant this was for rotating case, and not rotating, non-rotating are very different. So this is existing experiment. Current is very small regimes. They're trying to access the transition from non-rotating to rotating one, but as large Reynolds number, large Coriolis number, maybe it's different. So that is my last slide. I leave there for discussions and collaborations locally, and they'll be welcome. Thank you very much.
Thank you, Hantao, for that exciting talk. Are there any questions from the audience? Okay, let's take one from the front.
Yeah.
You mark Jupiter, Mercury, etc.
Yes.
That's of course not fixed in Coriolis number arbitrary number. It varies substantially from one place to another.
That's true. Okay.
So in fact, if you do that properly, it fills up almost the whole space. So I'm not exactly sure what you mean by putting it there, but we can discuss it.
Yeah, so actually there's another important, because we do have no gravity here. So we are talking about here, maybe it's around the equator only. Because you see, we don't have gravity help us.
I mean, there's differential rotation, there are all kinds of things.
This is for the interior.
Yeah, interior. I'm sorry. Yeah, not the.
Interior.
But of course, the main field effect should be part of the dynamo process, and we have no main field. This is just the gas centrifuge and the water centrifuge, and that is.
We can certainly go up in Rayleigh numbers up to about 17 or something like that. Going on the Coriolis number much higher is going to be difficult.
And yeah, we know gas centrifuge is it's a very advanced technology, and I don't know how much you want to access that for this purpose, for the security.
Helium 3 you're talking about?
Yeah,
Helium 3 is going to be very hard.
well, that's the gas water version is much easier, but the prime number is wrong. So I guess if we sacrifice prime number, we can have lots of fun with water without too much worry. Going to gas is always tougher, yeah. But I leave that for possibility. I'm not saying I'm committed already. I know I'm not, yeah.
Let's take another question. How about from there?
Yes, can I ask a naive question? So in pipe flow turbulence,
Yes.
neither Dwight nor I had time to mention this yesterday, but the instability is only excited after a particular amplitude has been reached, and it's known that that amplitude decreases roughly like 1 over Reynolds number, something like that. Yeah. Is there any similar thing conjectured for the astrophysical disk problem?
Well,
In other words, could it be that the reason that you see, no nonlinear hydrodynamic effect is simply because the amplitude needed to cause turbulence is just much too high at the Reynolds numbers we have?
So yeah, I have to be careful. Non-existence is different from weak.
I understand, yeah.
Yeah, so.
But we don't know if it's non-existent, right?
So I can't say non-existent because by definition of the measurements, it can't be 100% sure.
Right.
But good part of the numerical and the theory is your strength. You can take a bold step, see, you can challenge the question, how much is really doesn't exist? And how much lifetime, like we talked about yesterday. And if there's a perturbation created from beginning, how long it lasts before it dies away? What can make them cure it? That gives you a good idea why this should survive in higher or something.
Right. I mean, it also depends on what kind of perturbation you apply.
Yeah,
I mean,
that's
and
part. We don't have guidance.
For channel flows and things like this.
Channel flow, you have well-defined perturbation functions that you can fine-tune to let them less long. Here, have no idea, basically shooting in the dark. That's why we tried a couple of thousand different combinations. We thought helical could be, because it's helical.
Yeah.
Didn't make a difference. Maybe we tried too much, maybe had to be gentle. Yeah. There have been any guidance from experiment, from theory or simulations that give us a lot of easier time for experiment. So I wish we can be sophisticated like pipe flow experiment, but I couldn't because it's a lack of the theory part. Yeah.
That amplitude will be a radial distance, right? So I guess the answer would be if your amplitude is on the order of the rotation rate,
Mm-hmm.
right? Particularly the counter-rotating perturbations, then that should survive. I mean, numerical experiments do produce vortices if you put down strong enough vortices.
Yeah, so the lifetime, that's why I said decay. I was interested in measuring the lifetime, but turned out it was so fast every time. There's no distribution even. The PDF, I cannot contribute the constructed to PDF. Everything be cured immediately by the shear. So maybe there's a way to prolong the lifetime. Then we can understand which one is contributing how much. And then actually solid body is the most, but solid body is the uninterested case. So getting a little stuck there. I wish, yeah. That's maybe what kind of pair of vortices generate. And one survive, one killed, yeah.
The
Anticyclones, yeah.
Okay, looks like we'll have some more discussion for lunch. Let's thank our speaker again.
Thank you.
And thank you very much to the organizers giving me here the opportunity to talk about a word which I didn't know in the beginning of this year. So turbophoresis was not in my vocabulary. So I just wondered who has heard that before, who is dealing with turbophoresis here in the audience. Oh, okay. So we were looking at some effects of Brownian motion and then how thermal gradients can also introduce density gradients. And then when we saw similar things in turbulent simulations with embedded particles, we were just extrapolating this term and making from thermophoresis turbophoresis. And then my students did some Wikipedia research and then found at least 3 papers dealing with this. So every 10, 15 years, people are talking about this. And because I'm in the process of understanding what turbophoresis means and brings for us in our research, so I thought present it to you and have some interesting discussions about this. As you see already in my title slide here, so I'm interested in planet formation. You see our friend the Earth here and some other planets up there. And the big question in planet formation is how you can make little tiny dust grains like here and there, which are embedded in a gaseous turbulent nebula around a star into these 3 objects here, which are, we call it in astronomy, planetesimals. But if you talk to solar system people, then this would be a comet, this would be an asteroid, and this is a Kuiper belt object. So Ultima Thule, so New Horizons had a flyby that object earlier, much earlier this year. So the big question is how transform this material, and this is all now turbulence and particle and gas interactions. So turbulence then has basically 3 important impacts, which is the characteristics of the asteroids to explain their shape, multiplicity, composition, but you also want to understand here things like what is the mass distribution in the solar nebula. So if you observe a disk around a young star, then the mass distribution is not really favorable for planet formation. Too much mass is far out where you don't want to have planets, and you need the material much further in, and maybe it's just sufficient to have the planetesimals much closer in. And then, of course, everything in the end has to be tested by comparisons between our planet formation prediction models and, in the end, what our observers are finding. So this is my group in Heidelberg that I'm working with, and a lot of funding comes from the German Science Foundation, which I have to acknowledge here by full heart. So the outline of this talk looks roughly like this. So I already mentioned a little bit the role of turbulence which we need, what is so special about turbulence in disk around young stars, then planetesimal formation, and then we come to two important points. One is understanding trapping concentration of material, where there are three different possibilities. One is a linear instability leading to dust concentration. One would be flow features already in a fluid like zonal flows and vortices, and the third one is now the new thing, so this turbophoresis thing, so concentration via turbulent pressure equilibrium, so particles then having a turbulent RMS pressure which is getting equilibrated. And then, of course, what are the consequences for future research? Well, it will be that we need proper microphysics in our numerical simulations in all our studies, which then means here doing proper non-ideal MHD or even plasma physics, doing a proper thermal control of our material, and of course also looking at the dust evolution in that system. So why do we think that protoplanetary disks are turbulent? On the left side, you see an image of a protoplanetary disk by the Hubble Space Telescope. And in the lower right, you see the artist's impression. So it's a pretty thick thing which is sitting there. And if you compare this to disks in our solar system, then they are radically different. So this is a disk around Saturn. It doesn't have gas, it doesn't have turbulence, and therefore the vertical extent is much, much smaller. So it's just 10 meters or something like this. So this is what a protoplanetary disk should look like if there was no gas, if there's no turbulence. Everything would be sedimenting to the midplane. So going closer to a protoplanetary disk with a probe, then I imagine a disk to be just looking like this wonderful sandstorm here. And the sandstorm is already indicating one of the fundamental problems in planet formation, because in a sandstorm, the dust, the sand grains are not only transported, they are also colliding. And collisions between sand grains, which is also an important building material for planets, does not lead to sticking, but to grinding down. So in a sandstorm, you're not producing boulders and bigger stones by having things adhere, but you're just making very fine dust, which gets in your ears and eyes, and it's horrible, yes. So one has to overcome this somehow. The other problem is that even if you can grow to certain sizes, let's say you get up to millimeters in size, the material is not staying in the solar nebula. The solar nebula, just like the Earth atmosphere, has a vertical and radial pressure gradient. And this gas pressure gradient is then exactly the direction in which material wants to sediment. So just like hail grains in a thunderstorm eventually fall down to the ground, the same happens with our pebbles here. So they are just sedimenting into the star within a roughly short time scale. You see just on the order of a million years here. So some of the material is growing and then falling into the star. And if you think about pebbles, we always say pebbles, millimeter-sized, centimeter-sized material, but actually we are just referring to the aerodynamic properties. So a pebble in this context could also be a dust bunny, like you see here on the left side, and so just a big fractal object of ice and a big mixture. But for us, the only important thing is what is the coupling time to the gas, and then it doesn't matter whether you are fractal and large or compact and small. So only aerodynamic coupling time matters. These are numerical simulations of magnetorotational instabilities around a young star, and you see it's wonderfully turbulent, so velocities are going all over the place, and this is now the plasma beta, so you see also there fluctuations, so it's really a wonderfully developed turbulent state. So this means this part of turbulence is just diffusing things and transporting and momentum in a very nice fashion. But at least in some numerical simulations, people found the formation of coherent structures, even in ideal MHD simulations like you see here on the left side. So this was here Sebastian Froment and Richard Nelson who found here big vortices forming, and they only found the vortices, they are difficult to find, by their concentration of dusty material. So anticyclones in this and zonal flows are concentrating dusty material. They are concentrating our pebble and therefore preventing them to fall into the star. So why is this important? Because in this work here together with Mordecai, where are you? I heard your voice before this morning. Okay, you know this work already. Good. Good. So this is a simulation of a mini-rotational instability where this MHD instability has created a zonal flow in the background. And this zonal flow is here located at this direction. And you see already that way more material is at this distance than at any other distance. And now the dust grains are further getting accumulated into this trap in here. And we also have soft gravity solved in that simulation. And once we overcome a critical density, which is the Hill density or Roche density, starting from that value, the tidal forces from the star cannot disrupt you anymore. We find here the formation of gravitationally bound objects. So this was an MHD simulation. You can also do simulations in which you are threading your disk with a radial temperature gradient. And this radial temperature gradient is also driving the formation and amplification of vortices in a disk. This is a very similar process like temperature gradients in the Earth atmosphere are creating our weather and climate and everything. Also here we found then the formation of vortices in there. So this is now already the first big difference to what Han Tao was talking about this morning. So this was a disk in his sense, which is just hydrodynamic. So it has a barotropic equation of state. So there are no temperature variations, no vertical additional stuff in it. So, and a disk which has a proper thermal relaxation and which has a proper temperature gradient will then be forming these things. That's a slightly different instability here. It's called the vertical shear instability. So you see you need then a three-dimensional simulation. Natasha Manger has been doing that stuff in here. And if you plot the vorticity, then you find here in this chunk these anticyclonic vortices which are forming. So this was a parameter study that Natasha was doing for her PhD thesis, and she found that if just the box is large enough and resolution is good enough, then you are forming very long-lived particle traps in here. Good. Overall, the disk around a young star will be a really challenging problem. So because it's not just a question on how well your material is ionized, how strong the temperature gradients are, the entropy gradients, the thermal relaxation is, the Hall term comes into play. So it's a mixed bag of instabilities. But in the end, it will be a system in which all these instabilities will talk to each other and produce a combined picture of instability. So it's something I haven't mentioned yet is, for instance, the formation here then also of winds at the surface of an ionized disk, which is then also transporting angular momentum and forming structures in that stuff. Whereas then a good comparison is here on the lower left, you see a simulation which was ideal MHD. This is turbulence. But if you do non-ideal MHD, especially with the Hall term, voila, you're getting these wonderful structures like zonal flows and vortices in. Coming back to the two hydro instabilities that I'm talking about. So these are not nonlinear hydro instabilities. The important thing here is that both are linear instabilities. So the Rayleigh criterion states that the angular momentum has to decrease outward in order to be unstable. This is what you find here in the expression of the epicyclic frequency. kappa r square. So this is the radial epicyclic frequency, and this is the stabilizing force against our convective overstability. But because we are radially stratified in entropy, we have radial buoyancy, and we heard yesterday that convection is one of the most powerful energy sources in the universe. I like that. So you see that they are now in a struggle with each other. So this one means stability, this one means instability, and usually that guy wins. But we have a certain thermal relaxation time. Then you get into the business of these double diffusive instabilities. And this means that the unstable mode is then not just here an oscillation, but it's a growing oscillation over time, a radial oscillation. So for the vertical shear instability, it's completely different, but still exactly the same. In that case, it's just reversed. Now it's the vertical buoyancy which is stabilizing the system, but the vertical shear which is destabilizing it. And again, for the right thermal relaxation rate, everything is wonderfully unstable and is forming modes in here which are then vertically oscillating. And in a true system, then you have a mix of all different instabilities. So Thomas Feil, who has a poster and is also in the audience here, has mapped out where in a disk, so a U distance from the star and the height above the midplane, which instability might be operating. So some things that we are now looking closer into. So for people thinking about planetary atmospheres, it should not be a surprise that a disk wants to form rings and vortices, like any planet which we know is forming eventually vortices and zonal flows in there. So this is just a property of the rotation of the system itself. The method of planetesimal formation is then that material in such a disk is getting trapped in these blue circles here. These are then zonal flows and rings. You are concentrating material, you get streaming instability, collapse of material, and then you have your planetesimal. Remember, I showed you this movie before. The particles itself also deliver feedback to the gas. And this leads to a second class of instabilities, which is then basically the most important effect at the smallest scales, when the final body actually wants to contract into a planetesimal. So that's a final obstacle you have to overcome. Here you see, for instance, the Kelvin-Helmholtz instability, which is triggered by the feedback of particles to the gas. I'm just jumping slightly ahead. This is now a simulation of streaming instability, I would say. It looks like streaming instability, but it cannot be our linear streaming instability, which was so nicely studied by Udine and Goodman and others, because there is no vertical structure in that. But we still see that in this radial azimuthal two-dimensional simulation, the dust is fluctuating in its density, and the question is, why is that? So if we switch on gravity in that after some time, then we see that now gravity and diffusion are acting against each other, and see how the thing can collapse and contract. So it's a really slow contraction process, and in the end you see a denser and denser cloud here forming planetesimals in. So the idea is now turbophoresis. Classically, diffusion leads just to the equilibration of gradients, like you see in the upper left here. So if you have a density gradient, it's getting removed by turbulence diffusion. Turbulent diffusion is some length scales times the velocity, or a time scale times velocity squared. But particles do not couple perfectly to the gas. They have a finite coupling time. And if the coupling time is in the right ratio, smaller than the largest turbulence scales, time scales, then they are receiving an RMS velocity, a local RMS velocity, which is then just like the speed of sound or the molecular, the motion of the gas molecules on the smallest scales. So this is then basically when the continuum continuum approach, or for the dust density breaks down, and you have to consider the paths of individual particles. And on this smaller scales, the diffusion equation then has to be replaced by something by units. It's still the same, but then the RMS velocity of the particles goes to the density, and only the coupling time between particles and gas stays in front. And then you can identify this term here as just being the pressure, the turbulent ram pressure of particles. So we have done a range of streaming instability simulations. This is work by Marco Barth, a bachelor student. And then if you're plotting on the right side here the turbulent pressure, then you find this nice plateau phase here, in which then this particle turbulent pressure is constant over, let's say, two orders of magnitude of dust to gas ratio. So this leads to a concept then of equilibrium between pressure and gravitational contraction, very similar to star formation. We are forming a lot of planetesimals. We are further contracting them in additional simulations, and then to see what their properties are. You see here this contracting pebble cloud, which is then forming here a binary planetesimal. And if you want to know what shape they eventually have, we are also then switching to a different prescription of particle collisions, and then see how our pebbles are colliding with each other and forming bigger and bigger planetesimals, which are spinning, and which we can then compare to the actual findings here of our objects in the solar system. So you see at least the color is correct, which we have. On the shape we are working, at least the effect is obvious. Angular momentum conservation leads to elongated, flattened objects, bilobed objects, so exactly what you want to find. And by that I'm concluding my talk. So I talked about the importance of concentrating and trapping particles. There are at least 3 different methods for this, and in order to be able to trace all the physics in simulations and theoretical understanding, one needs the right microphysics. Without the right microphysics, one will not get the proper answers and understand planet formation. And by that, I thank you very much for your interest.
Thank you very much. Let's have some questions. So over there on the left-hand side.
Excuse me, do you use for describing turbophoresis this equation, because it's only the approximation?
Yes, absolutely. I was just simplifying things here to pedagogically explain the effects, right?
So you used the true equation of motion of the particle?
Yes.
Oh, okay.
Absolutely,
Thanks.
yes. Right.
Question from CL.
A more general question is that besides this turbulence driven by instabilities on the disk, and how about the turbulence from the collapsing cloud from background? What would be the effect on
So at the stage when the cloud is collapsing, by definition, it will be self-gravitating. So the collapse itself will bring a lot of motion in it. And then also when this mass has piled up and that the disk mass is more significant than the stellar mass, you will be in a very turbulent regime of self-gravity of the disk. You will have spiral arms. Think about a galaxy with its grand spiral structure, and this will be a very turbulent, short lasting time of, let's say, 10 to 4 years. And after that, if there's no additional turbulence, things will decay pretty rapidly. So if you have been able to form planets already in that very short time, like people exploring this for certain conditions, things are okay. But then after that, turbulence will very quickly decay.
Okay, any questions from online? Okay, if not, let's thank our speaker again.
Yeah, thank you for all the speakers for exciting talks. I guess today, morning session, we had a series of interesting talks from the variety of topics, focusing on from the terrestrial experiments to astrophysical probes of turbulence in interstellar medium, And so I decided to kind of look around. It's a very broad topic, and I tried to kind of zoom in on some of the key concepts that maybe we can discuss a little bit more about. Some of the theme that came up was the issues of high beta plasma, and our desire to learn more about this because of the broad applications that the high beta plasma will have in a variety of astrophysical contexts, and at the same time, our knowledge of high beta plasma is not quite there yet. We have had several talks on turbulence in interstellar medium, so we can have discussions about that. And we also had the talk from the Hantao on the laboratory studies of instability turbulence and its application to astrophysics. Turbulent mixing layers, we had a very nice talk on sort of the basic understanding of what is going on in these radiative turbulent mixing layers and how that might be applicable for astrophysics. And then we had an interesting talk on the turbophoresis, which we just heard about. So I will organize this into sort of 5 brief sections, approximately maybe 4 or 5 minutes each. And we can continue. We had a lot of discussions and questions. We can do more of this. I just put up some of the slides and summary that I've taken while I was listening to the talk. So just to kind of remind us of some of the takeaway points, but we can open the floor for the discussions. So maybe the issues about the high beta plasma, I think the motivation is pretty clear to all of us. The high beta plasma is ubiquitous throughout the universe, ranging from the solar winds to accretion disks around supermassive black holes. There are a lot of missing baryons in the universe that we haven't even kind of, got the observations of, but most of these gas in the outskirts of galaxies, galaxy clusters, and cosmic web that we have even yet to have observations are presumably made out of high beta plasma. So that's an application that's maybe for the future, or in several decades from now. So we can have the discussions about more for like a future outlook. And one of the main goals for the high beta plasma is to develop a predictive theory of how the plasma responds to different types of perturbation, how it causes the transport of mass, momentum, energy, and how it generates an amplified magnetic field and so forth. And so I think there are a number of maybe opportunities and challenges for tackling these big questions. Maybe some questions are in experiments and observational side. Maybe some are more in the theoretical computational side. What are some of the roles of machine learning? It occasionally comes up, and we're all excited about hearing more about how we can use machine learning even for this high beta plasma research, which we haven't talked too much about yet. So maybe we can open the floor for discussions and questions that anyone might have, or insights that you like to share about how we might go about actually understanding this high beta plasma. What are some of the exciting opportunities? Wow. Yes.
How high does beta actually get? Of course, there's always a magnetic field, and it's always dynamically important, so that kind of limits how high beta can get.
That's probably even the sort of discussion point for us to agree on what is high beta plasma. Would it have to be few, 10? In the case of diffuse gas in outskirts of clusters, could be easily 100. So it could be very high. Magnetic field could be low. In a galaxy cluster, the pressure is high. A magnetic field is few microgauss. So in the intermediate region, virialized regions of clusters, it's as high as 100. So it's kind of interesting applications to think about the theory. But we have plenty of observations, from X-ray to microwave observation, which causes these imprints in cosmic microwave background. And we can detect these gas, but they are high beta plasma. They are magnetized plasma that is causing a very diffuse, but still pretty high pressure in the galaxy cluster regions. So, and that is the theory that we need. We need to actually do simulations of those high beta plasma, and that's one of the major theoretical uncertainties in the ability to model those gas embedded within those dark matter halos. So, yeah, yes?
So on top of that, for instance, if you think about accretion flows, especially protoplanetary discs, then at the surface from plasma values around unity, it goes to 10 to 5, 10 to 6, whatever you want, towards the midplane.
a little bit surprised. I expect things like of order.
Can you use your seat mic, please?
Enormous. Yeah, sure.
Yes.
There's also potentially low beta regimes, right? So molecular clouds can be beta of around 1 or potentially even lower. So it's not only the high beta regimes that are important.
That's right.
Yeah.
Less understood. Yes, that's right. I guess we happened to hear about the high beta plasma talk. That's how we kicked off this particular session, which is just sort of why I've focused on it. But that's right. I think that low beta plasma is just as interesting, if not less understood.
One important question, I think, following on your question, is to ask, what do you mean by high and low beta? So where is the critical transition? If you're Hubert, it's around order 1, but that's, of course, a very vague number.
That's right. Yeah. Any thoughts on the transition for?
Okay. My question is maybe the solar surface serves as a transition area, right? You know, solar surface is high beta by definition. Dynamo working general magnetic field come out become low beta, whereas a different kind of physics shows up above the surface of the sun. So you want looking for the transition from high to low nearby surface of the sun is pretty good. Of course, we have lots of physics can be studied there, lots of the transition area or chromosphere, pretty rich partial ionization and radiation transport, different spectral lines.
Right.
Solar physicists enjoy this measurement a lot, but understanding still is very hard.
Right.
Yeah, complicated.
What are some of the challenges for the solar physics and that we might want to tackle in the maybe next decades or so? What are some of the outstanding challenges? Maybe that's one of the questions, maybe for more the experimental side, or they're more for the theoretical modeling issues?
But there are limits about they can resolve, right? Even sun is solar probe, I guess, is one of the good opportunity. But still, how much you can learn by observation? There's limit you can do. That's why theory, simulation, even experiment can work together. I would think, trying to solve problems together. Yeah.
Since you brought up galaxy clusters, it hasn't been discussed here, but the role of pressure anisotropy in very collisionless hot plasmas like the solar wind and galaxy clusters is super interesting, and experiments rarely get to that regime, in small laboratory conditions. But it would be great to have hot, very, very collisionless, highly anisotropic pressure, turbulence experiments at some point in the future. A solar wind tunnel or a wind tunnel for simulating galaxy cluster-like plasmas, high beta and collisionless, which is a hard regime.
Right. I think I think one of the interesting new directions that maybe we could go. This is sort of my since I happen to work on galaxy clusters, this is just one of the discussion that has been happening in the context of this thing called the Voyage 2050. There was a call from ESA. It's not just the Americans who's actually thinking about the future, but there's also the European version of thinking about what the future science should look like beyond 2035, where they already have the ideas for what the mission should look like. So they're looking the ideas beyond that. So everything that you will do until 2035 will be things that will be done, and then that think beyond that. So as a context of, and in a context of this white papers, I think there has been a meeting, I think in Spain. There are maybe 3 white papers that may be relevant for this audience here. One is the case for the electron astrophysics based on solar wind, and trying to launch the sort of new telescopes to study these questions related to things like electron heating or the magnetic reconnections in solar wind. But there are also the white papers on how to actually explore the detection of X-ray surface brightness. Currently, we're detecting things within these virialized region called R200, but the future mission, in principle, can significantly augment the detection all the way out to this, what's delineated here, going all the way out to accretion shock, where the infall velocity has Mach number of order hundreds. It's presumably collisionless shock, generating the pristine gas is actually shock heated, electrons are heated first, eventually actually the ions are heated first, and then through Coulomb collision, you will heat the electrons and so forth. So there might be an interesting sort of plasma physics that we might be able to do with this kind of mission. And similarly, using CMB as a backlight, one is also detecting the same hot gas, but using in a very different way in microwave. So there has been, I think, quite a bit of discussions and possible future directions. Quite a few, several decades from now. But that's something that maybe we can think a little bit more about as a way of learning about plasma physics or looking for new laboratories for plasma physics. Yes.
So when I go to plasma conferences, everyone talks about turbulence, but that turbulence is quite different from the turbulence we hear in astronomy environments. So I think it's important to distinguish turbulence because they have quite different properties in different regions, like this collisionless regime and this collisional regime, like interstellar medium, and also the processes that you mentioned here, like magnetic reconnection, particle acceleration, and they are different in different regions by interacting with the turbulence, that so-called turbulence.
I think that's a great point. We have a magnetized plasma atmosphere, so we have alphanic turbulence. We have a lot of bulk motions that are actually probably mixed with the actual hydrodynamic turbulence. So we have different types of motion that needs to be decomposed, and so that's maybe one of the topics that we should be discussing more is what is the definition of turbulence? What's the bulk and turbulent motions? How do you do the decomposition? Are some of the topics that we, I think, in our community, and especially when we start looking into the astrophysical laboratories, we need to be very clear about what we're measuring. Yes.
The thought that might be something interesting for Friday's unconference session, like if we could have a breakout group focused on what would a minimum definition of turbulence be? Is it just the 2-point function scaling, or do you have to go to some higher order statistics? And could there be some kind of minimal statistical definition for turbulence that we could mostly all agree upon? I think that might be kind of an interesting Friday breakout.
I completely agree.
It smells like turbulence. It's turbulence.
Yeah. And also the definition of low and high beta plasma and what the transition scale should be. Maybe another topic that we can discuss. Yes.
We had a lot of discussions about turbulence, but a lot of this turbulence in different circumstances, different environments, they're very anisotropic and they develop different spectra in different directions, which wasn't discussed at all. Another thing which I will be talking in my talk is that I didn't hear people discussing what determines the amplitude of the spectrum. It's not always energy cascade, it might be other things, and it might be more interesting than energy cascade because the slope of the spectrum, which is determined by other terms, may be higher than for longer spectrum, and these directions will accumulate more energy than other direction, and the structures which you see in turbulence may be determined by this energy which is accumulated in direction with higher energy slope. Okay, and we see it a lot of it in atmospheric and oceanic turbulence, but I'm sure the same thing will be true for other environments.
Yes.
It's another thing which is very important is that we always connect turbulence to dissipation rate, the Kolmogorov cascade. It doesn't need to be dissipation rate, it may be something else. Like in oceanic turbulence, we have sub-mesoscale.
Can you use your seat mic, please?
And energy which comes to sub-mesoscale, the rate of energy, it's maybe 2 orders of magnitude higher than energy which is dissipated on microscales. It's not the same kind of dissipation. And how this energy goes from sub-mesoscales and dissipates on macroscales, I don't think it's studied at all.
I think that's all very
studied very deeply.
important questions. I'm not sure if we will get to all of that question. We still have more than half the conference left. Hopefully we get to some of the questions along the way. But yes, that may be another possibly the unconferencing topic. We are accumulating very good questions here. Yes.
I think that it is related to driving the turbulence, and that I want to ask a question about there were a few talks, great talks on simulations of interstellar turbulence. So I wonder that how this numerical driving, I mean, whether it is satisfying or realistic to really simulate turbulence in our galaxy.
So maybe that's a good segue for the discussions on turbulence in ISM. We had 3 great talks. Maybe anyone who is willing to answer some of the questions for among maybe those of you who do simulations of ISM turbulence.
Yeah, I can address this.
Yeah, I guess it depends on the scale. So in principle, the best way would be to resolve all the scales relevant for driving, like from large scales on which instability set in, and drive turbulence potentially from the scales of galaxy scale height, and also resolve injection of energy by supernova and stellar feedback, and follow it down to smaller scales. I mean, this would be nice. Yeah, but unfortunately, so this sort of unfeasible. We need to like choose the dynamic. So we have like a limited dynamical range in simulation. So we necessarily need to choose like the box size and the resolution scale, which will set the dynamical range in the simulation. And then you either get realistic driving on large scales, either for the development of instabilities or injection of feedback or supernova or anything on small scales, but not the small scale dissipation of Pebbles, so vice versa. You need to put in driving by hand, and yeah.
And besides length scales, and how about the energy fraction? Like how much energy you put in solenoidal motions, how much energy you put in compressive motions? And I know that if the simulation is non-isothermal simulation, and there could be the change of the energy fractions along the cascade. You may have more and more solenoidal motions along the cascade. So eventually, when you go down to small scales, it doesn't matter. But in simulations, because of this limited initial range, driving does matter a lot. So how?
I agree. But again, so in large scale simulations like galactics, when you simulate entire galaxy, this should be like done. So you get like realistic fraction between the different driving modes automatically if you include realistic, if you model global dynamics of the galaxy realistically. But if you go to smaller scales, so there's like turbulent box simulation, it's a choice. You need to learn how exactly you drive these modes. What's the partition between different modes?
Okay, so there are 2 more questions over here. Yes.
Maybe I could make a remark on the effect of forcing on small scales in homogeneous isotropic turbulence, which appears in these calculations in exaggerated form in some fashion. Even though the forcing is initially low wave numbers isotropic, because the box is not really isotropic, it's a periodic box in 3 dimensions, 3 Cartesian dimensions. And also, for other reasons, there is a lingering anisotropy that goes through all the inertial range and dissipative, and even super dissipative, that is even beyond the Kolmogorov scale. And one way we can remove the anisotropy is by averaging over all possible directions. You can do that, or take project it on some SO3 or something like that. But the point really is that even for such an elementary case where there are presumably no complexities, you do have lingering effects of anisotropy forcing even at the very smallest scales, even if you resolve them very well. But I think we know how to take account of those in such flows, but it is very hard to see how in these simulations of galaxy, etc., if you force it in a certain way, it does not have any effect on others. I mean, it could have a huge effect.
Yeah, thank you. Yes.
I've never been working in astrophysics, but coming to point 3, I do simulations. question would be, what kind of Reynolds numbers are we talking about? Because that has an enormous input. And already for an airplane, we cannot afford it, and you're talking 10 to the power 8. So it seems to me that the point, first point under 3, subgrid turbulence and galaxy formation, looks like a terrible problem. I mean, very interesting, but I even wonder what are the basic guidelines. I suppose you are under-resolved by many, many orders of magnitude. So what would be a typical Reynolds number for galaxy formation simulation?
Vadim, would you like to take that?
I mentioned in yesterday, so the typical Reynolds number we have to deal with like 10 to the 10, about that.
Oh, I was expecting something much worse than that.
It's a real. Well, in simulations, even like in simulations, it's much worse. It's like hundreds, like maybe 1,000. In like driven box simulations, it's. Oh, real system is 10 to the 10. Yeah.
Some had Reynolds number of 10 power 10. Galaxy will have much higher.
Okay. Oh, I think this sounds like a great discussion topic over lunch. I think we're actually getting a little close to time. I still want to mention just a couple of topics that got covered, just to, the food of thoughts for us to talk more over lunch. Another topic that we just heard was the radiative turbulent mixing layers and analytical formulation of it. Variety of application from supernova winds to penetrating streams in galaxy formation. Number of questions has already come up. I think there's not enough time for us to discuss more about this topic. There are a lot of interest. So I suggest that we take this over to lunch and talk more about this. There were other topics that we also heard about, the terrestrial astrophysics lab connections. How can we apply what we're learning from terrestrial experiment and trying to understand, say, solar winds, or possibly even things like the ISM turbulence or galaxy clusters. And all of us, I guess, learned a new word, turbophoresis, which I think is a really interesting mechanism that leads to a variety of instability. And maybe this is one way to think about how to develop a sort of subgrid model. This old folklore of turbulence equal diffusion was debunked, and now we actually have to think about these additional turbulent pressure term that arises from these microphysics. So I think that's an exciting topic that I think we're learning more about, and how to sort of understand these phenomena of turbulence. So with overdue, I'd like to thank all the speakers and all the participants today, and let's take these discussions to the lunch. And thank you very much, everyone.